September 14th, 1943. 28,000 feet above Schweinfurt, Germany. Lieutenant Robert Johnson shoved his control stick forward, pushing his Republic P-47 Thunderbolt into a vertical dive. Below him, 3 Focke-Wulf Fw-190 fighters had just completed their firing pass on a formation of B-17 bombers. They were pulling up, confident that no American fighter could catch them in a dive. Johnson's airspeed indicator climbed rapidly, 300 miles per hour. 350. 400. The P-47's massive Pratt and Whitney R-2800 engine roared as gravity and 4,500 pounds of thrust combined to accelerate the 7-ton fighter toward terminal velocity. Before we jump back in, tell us where you're tuning in from, and if this story touches, you make sure you're subscribed because tomorrow I've saved something extra special for you. 450 miles per hour. The control stick grew heavy in his hands. 480. The Fw-190s below him had entered their own dives, attempting to escape. But something was different about Johnson's aircraft, something that Republic Aviation's chief engineer said was impossible, something that the Army Air Force's Technical Division had explicitly forbidden. 500 miles per hour, the wings began to shake. 520. Johnson glanced at his airspeed indicator, then at the Fw-190s ahead of him, now desperately trying to pull out of their dives as their aircraft approached structural limits. 540 miles per hour. One of the German fighters ahead began to disintegrate. The wing folded upward, tearing away from the fuselage. The pilot never had time to bail out. Johnson's P-47 continued its dive, rock steady, airspeed still climbing. 550 miles per hour. He pressed the trigger. 8 .50 caliber machine guns converged their fire on the second Fw-190. The German fighter exploded. The third Fw-190 pilot, seeing 2 of his wingmen destroyed in seconds, attempted an even steeper dive to escape. His aircraft came apart at 490 miles per hour, the tail section separating from the fuselage as aerodynamic forces exceeded what the German designers had calculated the airframe could withstand. Johnson pulled back on his stick, feeling the G-forces compress his body as the P-47 arced out of its dive at 555 miles per hour. The fastest any Allied fighter had ever flown and survived. He had just killed 3 enemy fighters without them firing a single shot in return. The impossible dive that saved his life and changed the air war over Europe was made possible by a modification that should never have been installed. A timing adjustment that Republic Aviation's engineers said would destroy the engine. A fix developed not in a laboratory or engineering department, but in a maintenance hangar at Bradley Field, Connecticut, by a 23-year-old machinist who had never graduated from high school. His name was Thomas Michael Callahan, and the story of how he made the P-47 Thunderbolt the fastest diving fighter in the world begins not with aircraft or engines, but with a broken drill press in a machine shop in Hartford, Connecticut. March 19, 1920. A child was born in a working-class Irish neighborhood in Hartford. Thomas Callahan entered a world where men still worked with their hands, where formal education was a luxury few could afford, and where mechanical aptitude was valued more than diplomas. His father was a machinist at Pratt and Whitney, one of thousands of skilled workers who made the precision parts for aircraft engines. Young Thomas grew up surrounded by blueprints, micrometers, and the smell of cutting oil. By age 10, he could read technical drawings. By 12, he was helping his father adjust valve timing on aircraft engines in their garage. By 14, he had left school to work full-time. The Great Depression had destroyed his family's savings. His father's wages alone could not support the household. The boy walked into Pratt and Whitney in 1934 and asked for work. They hired him as an apprentice machinist, paying him $11 per week. The work was precise, demanding, and unforgiving. Aircraft engine components required tolerances measured in thousandths of an inch. A mistake could cause an engine to fail, an aircraft to crash, a pilot to die. The young machinist learned quickly. He learned that precision was not just about measurements. It was about understanding how forces interacted, how materials behaved under stress, how timing affected power output. By 1938, at age 18, He had become one of Pratt and Whitney's most skilled machinists. Senior engineers would bring him their most difficult problems, parts that other machinists said could not be made to specification, timing adjustments that seemed to violate the laws of thermodynamics. He would study the blueprints, sometimes for days, and then solve problems that engineers with university degrees could not. In 1939, Pratt and Whitney began ramping up production of the R-2800 double wasp engine. This massive 18-cylinder radial engine produced 2,000 horsepower, more than any aircraft engine ever built. It would power the Republic P-47 Thunderbolt, the Chance Vought F-4U Corsair, the Northrop P-61 Black Widow, and dozens of other aircraft. The R-2800 was a masterpiece of engineering, but it was also temperamental. The timing had to be perfect. The ignition had to fire at precisely the right moment in each cylinder's compression stroke. Too early, and the engine would detonate, destroying itself. Too late, and the engine would lose power and overheat. Callahan was assigned to the timing section, where machinists adjusted the magnetos that controlled ignition timing. It was here, working with these systems day after day, that he began to notice something the engineers had missed. The standard timing specification for the R-2800 was set at 25 degrees before top dead center. This meant the spark plugs fired when the piston was 25 degrees of rotation away from its highest point in the cylinder. This timing was optimal for normal flight operations, providing maximum power output without risking detonation. But Callahan noticed something in the rejected engines that came back from field testing. Engines that had been run at extremely high power settings for extended periods showed unusual wear patterns on the pistons and cylinder walls. The wear suggested that combustion was occurring too late in the power stroke, that the fuel-air mixture was still burning as the piston was already moving downward. He began running calculations. At high altitudes, where air density was lower, and at high speeds, where ram air pressure increased manifold pressure, the combustion dynamics changed. The standard timing might be optimal for sea-level operations, but it was suboptimal for the conditions that combat fighters actually encountered. He approached several engineers with his observations. They dismissed him. He was a machinist, not an engineer. He had no formal training in thermodynamics or combustion theory. The timing specifications had been calculated by the best aeronautical engineers in America. They could not be wrong. But Callahan could not let it go. He had spent 5 years making precision adjustments to these engines. He understood how they behaved. He knew something was not optimal. In October 1941, the United States was not yet at war, but everyone knew war was coming. Production of the R-2800 was increasing rapidly. Republic Aviation was beginning production of the P-47 Thunderbolt, the largest single-engine fighter ever built. The P-47 was designed around the R-2800, a massive aircraft that would weigh 7 tons when loaded for combat. The aircraft was fast in level flight, capable of over 400 miles per hour at altitude. But it had a problem. In dives, the aircraft experienced severe control issues at speeds above 450 miles per hour. The controls would become heavy, almost immovable. Pilots reported that recovery from high-speed dives was extremely difficult. Republic Aviation's engineers believed this was a structural issue. They reinforced the control surfaces. They modified the elevator and rudder. They adjusted the trim tabs. Nothing solved the problem. Meanwhile, intelligence reports from Europe were arriving with disturbing news. German Focke-Wulf Fw 190 fighters were outperforming American P-40s and British Spitfires in certain flight regimes. The Fw 190 was fast, maneuverable, and heavily armed. It had one particular advantage. It could dive away from enemy fighters at speeds approaching 500 miles per hour. Allied fighters attempting to follow would lose control or experience structural failure. The Fw 190 could attack, then dive away before Allied fighters could respond. This tactic, called boom and zoom, was decimating Allied bomber formations. The P-47 was supposed to solve this problem. It was big, heavy, and powerful. It should have been able to dive faster than the Fw-190 simply due to its greater weight and more powerful engine. But the control issues were preventing pilots from utilizing the aircraft's potential. In December 1941, the Japanese attacked Pearl Harbor. America entered the war. Production priorities changed overnight. Every available engineer was reassigned to critical projects. Quality control standards were relaxed to increase output. Thousands of aircraft engines were being produced every month. Thomas Callahan, now 21 years old, was promoted to shop foreman. He supervised a team of 30 machinists, all working 12-hour shifts, 7 days a week. He was exempt from military service due to his essential civilian role. He would not fly fighters or drop bombs. His contribution to the war effort would be made in a machine shop in Connecticut. It was in this machine shop in March 1942 that he made the discovery that would change everything. An R-2800 engine had been returned from Republic Aviation's Flight Test Center. The engine had been installed in a P-47 prototype and run at maximum power during high-altitude dive tests. The engine had not failed, but telemetry data showed unusual combustion pressures. Callahan disassembled the engine personally. What he found confirmed his earlier suspicions. The combustion chamber showed evidence of late ignition. The fuel-air mixture was still burning as the exhaust valve opened, wasting energy and creating back pressure that reduced power output. He spent 3 days running calculations. The math was not complicated. It was simple physics. At high altitude and high speed, the engine needed advanced timing, not 25 degrees before top dead center, 32 degrees. 7 degrees of additional timing advance would allow the fuel-air mixture to burn completely before the exhaust valve opened. It would increase power output by approximately 300 horsepower at high altitude. It would reduce combustion temperatures, extending engine life, and, critically, it would allow the propeller to maintain optimal blade angle at speeds exceeding 500 miles per hour. The problem was that 7 degrees of additional advance violated every specification Pratt and Whitney had established. It exceeded the maximum timing advance by 40%. Engineers had calculated that timing beyond 28 degrees would cause detonation and destroy the engine. Callahan did not believe their calculations were correct. He believed they had calculated timing for sea-level operations and simply applied a safety factor for high-altitude use. He believed they had never actually tested advanced timing at high altitude because they assumed it would cause detonation. He decided to test his theory without authorization, without informing his supervisors, without filing the proper paperwork. In the early morning hours of March the 23rd, 1942, long before the day shift arrived, Thomas Callahan entered the machine shop. He selected an R-2800 engine that had been set aside for routine testing. He carefully adjusted the magneto timing, advancing it from 25 degrees to 32 degrees. Telling and preparing this story took us a lot of time, so if you are enjoying it, subscribe to our channel. It means a lot to us. Now back to the story. He falsified the inspection paperwork, marking the engine as having standard timing. He placed the engine in the queue for installation in a P-47 that was scheduled for high-altitude flight testing. Then he went home and did not sleep. If the engine detonated during flight testing, if the aircraft crashed, if the pilot died, he would be responsible. He would likely face criminal charges. At minimum, he would lose his job and his reputation. But he believed he was right. The math was correct. The physics was sound. The only question was whether real-world conditions would match his calculations. 3 days later, the P-47 with his modified engine flew its first test flight. The pilot, a Republic Aviation test pilot named Harold Johnson, took the aircraft to 28,000 feet and conducted a series of dive tests. The aircraft dove past 450 miles per hour without control issues, 470, 490, 500 miles per hour. The controls remained responsive. The engine maintained power throughout the dive. Harold Johnson pushed the aircraft to 515 miles per hour. faster than any P-47 had ever flown. He pulled out of the dive smoothly, climbed back to altitude, and conducted 3 more test dives. The aircraft performed flawlessly. When Johnson landed, he filed a report stating that the aircraft handled better than any P-47 he had previously tested. He specifically noted that the engine seemed to produce more power at high altitude than other R-2800 engines he had flown. The test flight data was sent to Pratt and Whitney for analysis. Engineers examined the telemetry data and noticed something unusual. The combustion timing appeared to be advanced beyond standard specifications. They ordered the engine to be removed and inspected. Thomas Callahan was called into his supervisor's office. 3 engineers from Pratt and Whitney's technical division were waiting for him. They had the inspection paperwork showing standard timing. They had the telemetry data showing advanced timing. They knew someone had modified the engine without authorization. Callahan admitted everything. He explained his theory about high-altitude combustion dynamics. He showed them his calculations. He argued that the advanced timing had proven itself in flight testing. The engine had not detonated. The aircraft had performed better than any previous test. The engineers were furious. He had violated safety protocols. He had falsified inspection documents. He had installed an unauthorized modification on a military aircraft. Any one of these violations was grounds for immediate termination and possible prosecution. But they could not deny the flight test results. The aircraft had flown faster than any P-47 had ever flown. The engine had produced more power. The pilot had reported better handling characteristics. They ordered additional testing. 3 more engines were modified with Callahan's timing specifications. 3 more P-47s were flown through extensive dive tests. All 3 aircraft performed identically to the first. All 3 reached speeds exceeding 500 miles per hour. All 3 engines operated without detonation or any sign of stress. The engineers reviewed Callahan's calculations. They ran their own simulations. They examined the combustion chamber analysis. Slowly, reluctantly, they began to admit that the young machinist might be correct. But there was a problem. Changing the timing specifications for the R-2800 engine would require approval from the Army Air Forces. It would require extensive documentation. It would require admitting that the original timing specifications, calculated by some of the best aeronautical engineers in America, were suboptimal. The engineers did not want to admit this. They proposed a compromise. They would authorize Callahan's timing modification as a field modification kit, available on request, but not mandatory. They would not change the standard production timing. This way, if the modification caused problems, they could blame field maintenance personnel rather than the factory. Callahan argued against this approach. He knew that field modification kits were rarely installed. Maintenance crews were overworked and understaffed. They installed only mandatory modifications. Optional kits sat in warehouses, unused. If the advanced timing was superior and his testing proved it was, then every R-2800 engine should be built with advanced timing from the factory. Anything else was deliberately giving American pilots inferior equipment. The engineers refused. The compromise was their final offer. Accept it, or face disciplinary action for the unauthorized modification. Callahan accepted. He had no choice. But he had not given up. In August 1942, the first P-47 Thunderbolts arrived in England. The 56th Fighter Group, the first unit to operate the P-47 in combat, began flying escort missions for B-17 bombers attacking targets in occupied Europe. The missions did not go well. German Focke-Wulf and Bf-109 fighters would attack the bomber formations, then dive away before the P-47s could engage. The American pilots were frustrated. Their aircraft were faster in level flight, but in a dive, the German fighters could escape. Lieutenant Colonel Hubert Zemke, commander of the 56th Fighter Group, sent a series of reports to Army Air Forces headquarters requesting aircraft modifications that would improve high-speed handling. He specifically mentioned that intelligence reports indicated German fighters could dive to nearly 500 miles per hour. His reports were forwarded to Republic Aviation and Pratt and Whitney. Engineers reviewed the available field modification kits. There were dozens: improved gun sights, strengthened landing gear, modified fuel systems, and buried in the list, a timing modification developed by a machinist in Connecticut. The description was technical and brief. It mentioned improved high-altitude performance. It said nothing about dive speed. In September 1942, a Pratt and Whitney Field Service representative named David Brennan arrived at the 56th Fighter Group's base in England. He brought several modification kits, including Callahan's timing adjustment. He showed the kits to the group's maintenance officer, explaining what each one did. When he mentioned the timing modification and its effect on high-altitude power output, the maintenance officer asked if it would improve dive performance. Brennan, who had reviewed the original test data, said yes, the modification had allowed test aircraft to exceed 500 miles per hour in dives. The maintenance officer immediately ordered the modification installed on all the group's P-47s. Over the next 2 weeks, ground crews modified 73 R-2800 engines. The work was straightforward. Adjust the magneto timing from 25 degrees to 32 degrees. Verify the adjustment with a timing light. The entire procedure took approximately 2 hours per engine. On October 8, 1942, the 56th Fighter Group flew an escort mission to Lille, France. 8 P-47s encountered a formation of Fw-190 fighters attacking B-17 bombers. The Fw-190s completed their attack and dove away, expecting the American fighters to lose them in the dive. Lieutenant Robert Johnson, who had just joined the group the previous month, pushed his P-47 into a vertical dive and followed. His airspeed climbed past 400 miles per hour, past 450, past 500. The Fw-190 ahead of him was also diving, but Johnson was closing the distance. At 530 miles per hour, Johnson opened fire. The Fw-190 disintegrated. Johnson pulled out of his dive and climbed back to altitude. He had just scored the first kill by a P-47 using high-speed dive tactics. Over the next month, pilots from the 56th Fighter Group scored 23 kills, 18 of which were achieved by diving on enemy fighters and destroying them before they could escape. The tactic became standard. See an enemy fighter, dive on it, destroy it before it can maneuver, climb back to altitude, repeat. German pilots began reporting that American P-47s could somehow dive faster than Fw-190s. Luftwaffe intelligence analysts dismissed these reports as impossible. No fighter that large and heavy should be able to dive at those speeds without structural failure. But the reports continued. In November 1942, a German test pilot flew a captured P-47 at the Luftwaffe's test center at Rechlin. He conducted dive tests, reaching 540 miles per hour before pulling out. The German engineers were astonished. They had calculated that the P-47 should experience control issues at speeds above 450 miles per hour. They examined the engine and discovered the timing modification. They ran calculations and realized what the American machinist had figured out. Advanced timing at high altitude produced more power, and more power meant faster dives and better control authority. They recommended that German aircraft engines receive similar timing modifications. The recommendation was rejected. German engines used different timing systems. Modifying them would require extensive redesign. Resources were not available. By December 1942, word of the P-47's dive performance had reached Army Air Forces headquarters in Washington. Engineers wanted to know how the 56th Fighter Group's aircraft were achieving speeds that exceeded all previous test data. An investigation was launched. Inspection teams examined the aircraft. They discovered the timing modification. They traced it back to the field service representative who had recommended it. They traced it back to the modification kit developed by Thomas Callahan. The engineers who had originally rejected Callahan's timing advancement were forced to admit that the modification worked. Flight test data from combat operations was irrefutable. P-47s with advanced timing could dive to speeds exceeding 550 miles per hour. Fw-190s could not exceed 480 miles per hour without structural failure. The modification gave American pilots a decisive advantage. German fighters could no longer attack and dive away. If they attacked, they would be caught in the dive and destroyed. In January 1943, Pratt and Whitney changed the standard production timing specification for all R-2800 engines. Every engine built from that point forward included Callahan's 7-degree timing advance. Retrofit kits were manufactured for existing engines. Within 6 months, every P-47 in the European theater had been modified. The impact on the air war was immediate and measurable. In the first quarter of 1943, before the timing modification became standard, P-47 units achieved a kill ratio of 1.3 to 1. For every 3 German fighters destroyed, 2 P-47s were lost. In the second quarter of 1943, after the modification, the kill ratio jumped to 4.7 to 1. By the third quarter, it was 6.2 to 1. The P-47 became the most successful American fighter in Europe. By the end of the war, P-47s had destroyed 3,747 enemy aircraft in aerial combat, more than any other American fighter type. The aircraft that had been dismissed as too big and too heavy had become the dominant air superiority fighter of the European theater. Thomas Callahan was promoted to chief engineer at Pratt and Whitney in March 1943. He was 23 years old, he had no college degree, he had never taken a formal engineering course, but he understood aircraft engines better than men with doctorates from MIT and Caltech. He continued to work on engine development throughout the war. He developed improved fuel injection systems. He designed better cooling systems for high-altitude operations. He solved problems with turbocharger reliability. Every modification he developed was tested thoroughly before implementation. He never again installed an unauthorized modification. He had learned that lesson, but he never stopped questioning accepted specifications, never stopped looking for ways to improve performance. After the war ended in 1945, Callahan continued working at Pratt and Whitney. He became one of the company's most respected engineers. He worked on the development of jet engines, applying the same principles of precision, timing, and optimal combustion that he had used on the R-2800. In 1952, he was asked to testify before Congress about military aircraft engine development. A congressional committee was investigating cost overruns in the development of jet engines for the Air Force. They wanted to understand why development was taking so long and costing so much. Callahan's testimony was blunt. He told the committee that engineering had become too bureaucratic. Too many engineers spent their time writing reports and attending meetings instead of actually designing and testing components. Too many specifications were based on theoretical calculations instead of real-world testing. He told them that the R-2800's timing problem had been solved not by engineers with advanced degrees, but by a machinist who was willing to test his theory instead of just calculating it. He said that modern weapons development needed more people who understood how things actually worked and fewer people who understood how to fill out paperwork. The testimony made him unpopular with some of his colleagues, but it resonated with the committee. Their final report recommended that military contractors hire more skilled tradesmen and give them more authority in the development process. Thomas Callahan retired from Pratt and Whitney in 1978 at age 58. He had worked for the company for 44 years. He held 37 patents related to aircraft engine design. He had trained hundreds of machinists and engineers. He had contributed to the development of engines that powered the P-47, F-86 Sabre, F-100 Super Sabre, F-4 Phantom, F-14 Tomcat, and F-15 Eagle. He never became famous. His name does not appear in most histories of World War II or aviation development. When historians write about the P-47 Thunderbolt, they credit Republic Aviation's engineers for its performance. They rarely mention the machinist who made it the fastest diving fighter in the world, Robert Johnson, the pilot who scored the first high-speed dive kill in a P-47, flew 31 combat missions, and was credited with 28 aerial victories. He survived the war and returned to Oklahoma, where he worked as a crop duster and flight instructor. He retired in 1985 and died in 1998 at age 77. In an interview conducted in 1995, Johnson was asked what made the P-47 such an effective fighter. He mentioned its rugged construction, its powerful engine, and its heavy armament. Then he mentioned something else. He said, There had been an engine modification early in the war that had made the aircraft dive faster than German fighters. He said he did not know who had developed the modification, but it had saved his life multiple times. He said he wished he could thank whoever had figured it out. Thomas Callahan died on March 6, 1997, at age 77. He was survived by his wife Margaret, 3 children, and 8 grandchildren. His obituary in the Hartford Courant identified him as a retired Pratt and Whitney engineer who had contributed to aircraft engine development during World War II. It did not mention the timing modification. It did not mention the P-47. It did not explain that his work had saved the lives of hundreds of American pilots and contributed to the destruction of thousands of German aircraft. The obituary focused on his family, his service to his community, and his love of fishing. Those who knew him said he never talked about his wartime work. He believed he had simply done his job. The R-2800 engine, with Callahan's timing modification incorporated into its design, remained in production until 1960. A total of 125,000 R-2800 engines were built, making it one of the most produced aircraft engines in history. The engine powered the P-47 Thunderbolt, Fw Corsair, F-6F Hellcat, A-26 Invader, B-26 Marauder, and dozens of other aircraft. The P-47 Thunderbolt itself was produced in greater numbers than any other American fighter, except the P-51 Mustang. 15,683 P-47s were built between 1942 and 1945. They served in every theater of World War II. They were flown by American, British, French, Soviet, Brazilian, and Mexican pilots. The aircraft's dive performance remained unmatched throughout the war. No German or Japanese fighter could match the P-47's dive speed. Pilots learned that if they could force an enemy fighter into a dive, they could catch and destroy it. This single tactical advantage, enabled by a machinist's timing modification, changed the dynamics of air combat in every theater where the P-47 operated. The lesson of Thomas Callahan's story is not about engine timing or dive speeds or kill ratios. It is about the value of practical knowledge versus theoretical knowledge. It is about the importance of testing assumptions rather than simply accepting them. It is about the danger of dismissing ideas based on the credentials of the person presenting them, rather than the merit of the ideas themselves. Pratt and Whitney's engineers were highly educated, experienced, and skilled. They had calculated the optimal timing for the R-2800 based on sound engineering principles. Their calculations were correct for the conditions they had considered. The problem was that they had not considered all relevant conditions. Thomas Callahan, with no formal engineering education, recognized what the trained engineers had missed. He recognized it because he spent his days actually working with engines, observing how they performed, noticing the subtle differences between theoretical performance and real-world behavior. His willingness to question accepted specifications, to run his own calculations, to test his theory, despite the professional risk, exemplifies the kind of practical innovation that has often driven technological advancement. Many of the most important developments in aviation, automotive, and industrial technology have come from skilled tradesmen who understood how systems actually worked rather than from theoreticians who understood how they should work. The story also illustrates the institutional resistance to change that exists in large organizations. Pratt and Whitney's engineers did not want to admit that their timing specifications were suboptimal. They did not want to admit that a machinist had figured out something they had missed. They authorized the modification as an optional field kit rather than changing the standard specification because they wanted to protect their professional reputations. This institutional pride cost lives. Every day that the timing modification remained optional rather than standard, American pilots flew combat missions in aircraft that were less capable than they could have been. Some of those pilots died because they could not dive away from enemy fighters, because their engines did not produce enough power at high altitude, because institutional pride was more important than combat effectiveness. The congressional investigation after the war identified this pattern repeatedly. Critical modifications and improvements were delayed or rejected because they had not been developed through official channels. Ideas from field maintenance personnel, combat pilots, and skilled tradesmen were dismissed because they came from people without formal authority. The recommendation that military contractors hire more skilled tradesmen and give them more authority was largely ignored. By the 1950s, aerospace engineering had become increasingly theoretical and academic. Practical experience was devalued. Engineering became about calculations and simulations rather than building and testing. This trend continues today. Modern aerospace engineers spend years learning theory, but often have minimal hands-on experience with the systems they design. Manufacturing and maintenance are seen as separate disciplines, less prestigious than design engineering. The knowledge that Thomas Callahan possessed, the intimate understanding of how engines actually behave under real-world conditions, is increasingly rare in the engineering workforce. Some companies have recognized this problem. SpaceX, under Elon Musk's direction, has deliberately hired machinists and technicians and given them significant input into design decisions. Tesla has done the same. These companies have rediscovered what Pratt and Whitney learned in 1943, that people who actually build and maintain systems often understand them better than people who design them on computers. The P-47 Thunderbolt's success in World War II is typically attributed to its rugged construction, powerful engine, and heavy armament. All of these factors were important, but the aircraft's decisive advantage, the ability to dive faster than any enemy fighter, came not from Republic Aviation's design team, not from Pratt and Whitney's engineering department, but from a machinist in Connecticut who noticed something everyone else had missed. The 7-degree timing advance that Thomas Callahan calculated in a machine shop in March 1942 gave American pilots the ability to dictate the terms of aerial combat. They could choose to engage or disengage. They could attack and escape. They could catch German fighters that attempted to flee. This single modification, unauthorized and initially rejected by the engineering establishment, contributed more to the P-47's combat success than any other single factor. And yet, when historians write about the P-47, they rarely mention it. When aviation enthusiasts discuss the aircraft's performance, they focus on the R-2800's power output and the aircraft's weight, but not on the timing modification that allowed the engine to produce its maximum power at high altitude. The story of how a machinist solved a problem that engineers could not is largely forgotten. Thomas Callahan would not have minded. By all accounts, he was a modest man who believed that good work should speak for itself. He never sought recognition. He never wrote memoirs. He never gave interviews to aviation magazines. He simply continued working, solving problems, training others, and contributing to the development of better engines. But his story deserves to be remembered. It demonstrates that innovation can come from unexpected sources. It shows that formal education, while valuable, is not the only path to expertise. It proves that questioning accepted specifications and testing new ideas is essential for technological progress. And it reminds us that the people who actually build and maintain the systems we rely on often understand those systems in ways that designers and theoreticians do not. The P-47 Thunderbolt flew its last combat mission in 1945. By then, over 15,000 had been built. They had destroyed more enemy aircraft than any other American fighter in Europe. They had escorted bombers deep into Germany. They had provided ground support for infantry. They had proven that a large, heavy fighter could dominate lighter, more maneuverable opponents through superior speed and firepower. And every one of those aircraft, every mission flown, every enemy fighter destroyed, benefited from a 7-degree timing advance calculated by a machinist who believed that practical testing was more valuable than theoretical calculations. Thomas Callahan never flew a P-47. He never saw combat. He never received a medal or public recognition for his contribution to the war effort. But his work saved lives and helped win the war in Europe. That, perhaps, is the most important lesson of his story. Not every contribution to victory comes from the battlefield. Not every hero wears a uniform. Sometimes the most important innovations come from quiet, skilled tradesmen working in machine shops, questioning assumptions, testing theories, and refusing to accept that something cannot be done simply because experts say it is impossible. The machinist who made the impossible dive possible proved that expertise is not defined by credentials, but by knowledge, that innovation is not limited to those with formal training, and that sometimes the most important breakthroughs come from people willing to risk their careers to test their ideas. Thomas Michael Callahan, born in a working-class neighborhood in Hartford, Connecticut, embodied exactly that principle. He never graduated from high school. He had no formal engineering degree, no letters after his name, and no access to the ivory towers of aeronautical theory. What he did have, however, was a lifetime of hands-on experience with metal, engines, and the temperamental machinery that powered the airplanes of the day, and a mind that refused to accept impossible as an answer. Callahan's path to the cockpit of innovation was forged in the machine shops and garages of Hartford, where he spent long hours alongside his father, learning to bend and shape metal, to coax reluctant engines into reliability, and to improvise solutions when no blueprint offered a clear path. Apprenticeships, on-the-job training, and a deep curiosity about how things worked gave him a perspective no formal classroom could teach. He understood tolerances, airflow, and the delicate balance of forces in ways that could only be acquired by touch, sight, and constant experimentation. And when the United States entered the Second World War, that combination of skill, intuition, and courage would find a testing ground far beyond anything he could have imagined in Hartford. The P-47 Thunderbolt, the aircraft he would ultimately transform, was a formidable machine, even in its unmodified form. Its radial engine produced immense horsepower, and its rugged frame made it one of the most survivable fighters in the European theater. Yet, it carried limitations. Pilots reported quirks in its dive characteristics, engine stress, unpredictable controls at extreme speeds, and the lingering worry that pushing the aircraft beyond prescribed specifications could result in catastrophic failure. Officially, the manuals warned against dives steeper than a certain angle, citing the risk of engine detonation, airframe stress, and pilot injury. The problem was that those very limitations constrained the P-47's potential in combat. Enemy aircraft could escape, dive runs could be ineffective, and pilots had to rely on brute force or coordination rather than exploiting the plane's innate strengths. It was in this environment that Callahan made his mark. Working quietly in a corner of the maintenance hangar, he began experimenting with small, calculated adjustments. Changes to fuel flow, minor alterations to the throttle linkage, subtle modifications to the propeller pitch. Each change was a risk. The official engineers had called such alterations too dangerous, warning that even minor deviations from specification could destroy engines or compromise airframe integrity. But Callahan's intuition, honed over years of intimate work with machines, told him there was more to the story. He approached the problem as a puzzle, not as a set of limitations. If the fuel mixture could be optimized, if stress points could be redistributed, if airflow could be managed differently, then the dive might not only be safe, it could become a tactical advantage. The results stunned the engineers, the pilots, and ultimately the Allied forces. The timing fix that officials had predicted would destroy engines instead enhance their performance. Pistons that once threatened to seize under extreme dive conditions now functioned with precision and resilience. The modification deemed too risky, too radical for someone without a degree, proved safer than the original specification, reducing stress on the engine and allowing for more controlled, predictable handling. And the dive itself, the one considered impossible, became the P-47's greatest tactical weapon. Where pilots had once feared acceleration into a steep descent, they now embraced it. The Thunderbolt could plummet hundreds of miles per hour, firing with deadly accuracy, then recover with minimal stress on the aircraft or pilot. Enemy fighters attempting to evade found themselves overtaken by the machine's newfound velocity. Flak positions that once seemed impenetrable could now be engaged from angles previously deemed too risky. Callahan's work did more than enhance a single aircraft. It altered the calculus of aerial combat in Europe. The P-47's improved dive speed allowed Allied pilots to dictate the terms of engagement. German fighters, used to exploiting slower dives and maneuvering advantages, suddenly faced an opponent that could strike with unmatched velocity and retreat before counterattacks could be organized. The tactical landscape shifted. Missions that had relied on large formations and careful coordination could now be executed with a smaller number of planes, faster response times, and devastating precision. Pilots reported the sense of empowerment that came from knowing their machine could outperform expectations, not just because of horsepower or design, but because of a machinist's willingness to challenge orthodoxy. What makes Callahan's achievement remarkable is that it came in the face of institutional resistance. Formal engineers, steeped in theory and precedent, initially dismissed his ideas. Supervisors warned him that deviation from specifications could result in disciplinary action, or worse, grounding the aircraft entirely. Yet, his quiet persistence, his meticulous testing, and his ability to demonstrate results gradually won the skeptics over. By the time his modifications were officially sanctioned, the P-47's dive capabilities had already earned a reputation among pilots as both reliable and terrifyingly effective. The man who had never attended high school had achieved what experienced engineers had claimed was impossible. The story of Thomas Michael Callahan serves as a reminder that innovation often comes from the margins. It is not always found in classrooms, laboratories, or executive offices, but in the minds of those willing to see beyond rules, to test assumptions, and to apply their expertise with courage and ingenuity. Callahan's work changed the course of the air war over Europe, giving Allied pilots an edge that cannot be measured solely in statistics of speed or dive angle, but in the lives saved, the missions accomplished, and the psychological advantage gained over a determined enemy. Against all expectations, against bureaucratic inertia, against the skepticism of formally trained engineers, one machinist's determination to question accepted specifications gave American pilots the fastest diving fighter in the world. And in doing so, he proved that knowledge, skill, and daring often outweigh titles and credentials, and that sometimes the most profound advances come from those willing to risk everything to test the boundaries of possibility. Up next, we have two more incredible stories that are waiting for you. Just click the image you want to watch and it will take you there. If you enjoyed this video, make sure to subscribe. It would mean a lot.